Hello everyone, I welcome you all in this course Introduction to Sequence Stratigraphy, and we are discussing on the basic concepts of different sequence stratigraphic elements, where we are discussing about different types of system strats, different types of surfaces, and also we have tried to understand the different types of sequence in last few classes. So, this class is the last part of this series of discussions under this broad topic basic concepts of sequence stratigraphic elements, and in this class we are going to discuss about another element which we have not mentioned at all so far during our entire discussion, and that particular term is parasequence. So, parasequence is another very commonly used, very popularly used terminology in sequence stratigraphy, and it is very often used by many workers across the world, and that has also led to some sort of confusion, some sort of kind of doubts regarding the actual concept of parasequence. Several people have described parasequence in different ways from different areas, from different successions, and as a result of that there has been a lot of questions, there is a lot of problems regarding the actual definition, actual delineation of parasequences from sedimentary successions. So, there is another school which often try to avoid this parasequence approach. However, in this particular course, as we are going to cover up all the aspects of sequence stratigraphy within this course Introduction to Sequence Stratigraphy, so it will be a good option that we should have at least some idea, some basic idea about the concept of parasequence. So, in this class I will just give you a broad overview about this concept of parasequence, how we define a parasequence and how we apply that, use that in understanding the stratal stacking pattern, in understanding the system strats. But I will not go into the detail of that because that will lead to several debates or several questions. So, we will avoid that part. So, we can start with the basic definition of parasequence. So, a parasequence is a stratigraphic unit which is defined as a relatively conformable succession of genetically related beds or bed sets bounded by marine flooding surfaces and their correlative surfaces. This is a very basic definition, and in this definition we are getting three important terms. Number one, this is genetically related, first one. So, conformable succession of genetically related, this is number one. And genetically related what? Not about the stratal package, but we are talking about beds or bed sets. So, that indicates we are looking into much higher resolution, we are looking into smaller units within the sedimentary succession where we are trying to define parasequence. And the third important term is they are bounded by marine flooding surfaces. So, apparently marine flooding surface, if I abbreviate it, it will appear as MFS, but this MFS is not the MFS that we have discussed under the sequence surfaces or the system strat surface like maximum flooding surface. The abbreviation MFS stands for maximum flooding surface, which we have already defined in our previous classes. So, in this class when we are defining or discussing about the parasequence, we are dealing with marine flooding surface, or very commonly it is called as simple flooding surface. So, to define a parasequence, we have to find out two important parameters. Number one, conformable succession of genetically related beds or bed sets, and second one, we have to define a flooding surface which is a marine flooding surface or their correlative surfaces. So, when we are trying to define a parasequence, this particular term, the relatively conformable, this is very important term because we are dealing with beds or bed sets, we are not dealing with the entire succession, we are dealing in bed scale features, bed scale succession. So, in that particular scale, when we are talking about relatively conformable, that means that within the parasequence there can be brief interruptions in terms of the deposition, there can be small breaks in terms of deposition, which often we call as diasteme, but there should not be any unconformity, there should not be any major erosional surface separating these beds or bed sets, and it contains no substantial periods of erosion or non-deposition. So, when you are talking about these relatively conformable beds or bed sets, that means the beds were deposited without any major break. This is number one. Second, we are talking about genetically related beds or bed sets. So, in bed scale, when we are talking about genetically related, that means we are talking in terms of the facies. So, all the facies which are formed within a parasequence, which are present within a parasequence, they were deposited in lateral continuity to one another. So, when we get this kind of laterally continuous facies occurring one after another, we can call them as genetically related. So, these two parameters are very important to define a parasequence. So, it comes within the bed scale, where beds are in terms of facies which are genetically related and they are conformable in nature, they are not showing any major break during the deposition. So, when we talk about parasequences, definitely their scales are much smaller with respect to a systems tract or with respect to a sequence. So, commonly parasequences span in terms of meters to tens of meters, and they commonly represent durations of tens to hundreds of thousands of years. So, definitely in terms of the amount of time interval, they are of relatively smaller time interval, and definitely within that smaller time interval, they will produce thinner successions which may range in terms of meters to tens of meters. Commonly, a parasequence will represent a single episode of progradation. So, what we get within a parasequence, always it should be a coarsening upward prograding lobe. So, how we will define a parasequence? We can define a parasequence like, if I draw it like this, there is a succession in terms of multiple beds, and those beds will gradually show prograding succession like this. So, overall it will be a coarsening upward, a prograding upward lobe type succession, coarsening upward succession always. So, once this is over, say if I draw in a smaller scale, so you are getting one such coarsening upward succession, then it is covered by one surface, that is the break, and then again we are starting with another fine grained succession, fine grained beds, and it is again going up to another coarsening upward succession. Again it is starting with a very fine grain and ending up with another coarsening upward succession. So, each of these coarsening upward succession which indicates a progradation. So, we are getting multiple progradational lobes stacked one after another, separated by a surface which is starting with a very fine grained succession, a fine grained sediments. So, this kind of stacking of multiple vertical succession in beds or bed set scale, so they will be called as parasequences. So, this is one parasequence, this is another parasequence, this is another parasequence. Most parasequences are asymmetrical in nature. They are sallowing upward always, and within that sallowing upward character, sallowing upward nature within one particular parasequence, they show asymmetricity in terms of the occurrences of the sedimentary cycles. In the lower part of the parasequence, commonly we get dominance of the fine grained sediments, and those portions are commonly thinner within the overall parasequence. As we move upward within the parasequence, the sallowing upward part will be much more thicker with respect to the deepening upward part. So, within the lower part of the parasequence, we will get a deepening upward part which will be very thin, and that will change up into a sallowing upward portion which will be much thicker. within each and every parasequence. So, these are the characteristic of parasequences. So, I can tell you again, just to summarize, parasequences are succession of beds or bed sets which can span in terms of meters to tens of meters in thickness, which will represent time duration in terms of tens to hundreds of thousands of years. Each parasequence will represent single episode of progradation. That means they should be represented by coarsening upward prograding lobes. Such prograding lobes definitely will indicate seaward shoreline movement, and within each parasequence we get asymmetric cyclicity in terms of lower part confined by deepening upward portion, which will be thinner, and the upper part of the succession will be covered by shallowing upward portion, which will be much thicker with respect to the lower part. So, these are the basic characteristics of any parasequence. Now, when these prograding lobes are getting deposited, the deposition of each and every prograding lobe is terminated by event of abrupt water deepening. So, that water deepening, that abrupt water deepening will terminate this prograding succession and will lead to formation of or start of deposition of a new succession, new parasequence with again a deepening upward succession. So, what we get over here? A boundary demarcating the changeover from the coarsening upward to start of a fining or deepening upward succession, shallowing upward to a deepening upward succession. So, that sudden deepening across that particular surface leads to the formation of the marine flooding surface. So, how can we identify a marine flooding surface? There are several ways, I will tell you about that. So, commonly across a marine flooding surface, the rocks lying above and below, they commonly represent non-adjacent facies. So, when one parasequence is ending up, it is definitely ending up with very shallow succession, shallow sediments, and they are very coarse grained sediments. Then suddenly there is an abrupt water level rise, so abrupt deepening, and that deepening is leading to low energy condition, that deepening is leading to deposition of fine grained sediments. So, definitely the facies or the depositional condition across that surface, just underlying that surface and overlying that surface, will be drastically different. So, they will indicate or represent non-adjacent facies across the flooding surface. Say for example, we can say in the lower part we can get a foreshore sand. So, a parasequence is ending up with foreshore sand. We know that foreshore is a high energy condition, and there the sand that will get deposited will be relatively coarser grained, very well sorted. Now, that can abruptly overlain by an offshore mud, maybe offshore shale. So, when that offshore mud is directly overlying the foreshore sand, it will indicate abrupt deepening. So, it will indicate a marine flooding surface over there, and definitely across the marine flooding surface we are getting two different types of facies. They are not adjacent to each other. Foreshore sand is directly overlain by offshore shale. Similarly, we can get a distributary mouthbar sand deposit in a delta system. So, in the delta plain area, distributary mouthbar sand, or maybe in the just mouthbar is forming in front of the delta plain, where we get very coarse grained sand. So, when these delta lobes are moving forward, the delta system is progressing forward, we get multiple such mouthbars are forming. So, on the delta plane, the top part will be the mouthbar, which will be the coarsest sand, and then there is an abrupt water level rise, abrupt change in water depth, which will lead to increase in the water depth, and that can lead to the deposition of prodeltaic mud over that mouthbar sand. So, again we will get a surface across which we are getting abrupt changeover in terms of deepening, in terms of the facies type. So, in that case, mouthbar sand, which is far away from prodelta condition, will be directly overlain by a prodeltaic mud condition that will indicate a drastic changeover in terms of the energy system, in terms of the water depth. So, across the flooding surface or marine flooding surface, we cannot apply Walther's law. I think all of you can remember we discussed during our class on phases and phases analysis the application of Walther's law. So, across this parasequence boundary, the marine flooding surface, we cannot apply the Walther's law because there we get completely abrupt changeover in terms of the phases occurrences, and those phases which are non-adjacent will come over one another. So, how can we define a flooding surface? The flooding surfaces are subcontacts which separate the underlying shallow water phases from the overlying deeper water phases. I have just given you the example, say within one succession, maybe up to this is a delta lobe is forming, delta is prograding. So, over here we are getting delta mouthward deposit, and on that suddenly across this surface we get a sudden change in the water depth, and these shallower phases, this mouth bar, delta mouth bar deposit is overlain by pro delta mud. So, this mouth bar is a coarse grain sand and this is a mud. So, abrupt change in phases, this is pro delta mud. So, this is much deeper, this is mouth bar sand, this is much shallower. Similar kind of example can be shown from the foreshore and offshore. So, in any marine system we know if this is the marine system, then this part is the foreshore area very close to the shoreline, just in between the mean high water level and mean low water level, whereas offshore is somewhere very deeper which is beyond the storm wave base. So, we can get a foreshore sand overlain by this offshore mud. So, this phases is directly coming over here. So, there is an abrupt deepening, abrupt shift of the phases across this particular surface. So, when we can define this kind of coarsening upward succession followed by this kind of abrupt changeover in terms of shallower water phases in the underlying position and the deeper water phases in the overlying position, we can define this surface as a marine flooding surface. So, as the term is indicating marine flooding surface, so definitely we can identify these within marine successions only. We cannot identify these successions within continental systems. So, there are certain criteria apart from getting this shallower and deeper phases architecture across the surface, we can also identify flooding surfaces from several other features which may get associated with this phases changeover. For example, there can be small scale erosions usually of a meter or less which can be associated with this deepening effect. So, definitely water is rushing in, water is coming into the system on this shallower part. So, during that phase we can get some sort of erosions may go on, exactly like the kind of erosion we expect during the transgression forming the ravinement surfaces. So, similar kind of erosional event can occur at the base of these flooding surfaces. Sometimes the flooding surfaces can be represented by a transgressive lag. That means the water body is coming in. So, across this surface, if this is the flooding surface, then along the bottom of this surface we can get some sort of transgressive lag deposits which are very thin, less than a meter in thickness, and commonly composed of shales or mud ripups or calcareous nodules depending on area to area. So, that can also an additional feature to identify a flooding surface. Third, we can get some characteristic ichnofacies. For example, we can get glossy fungites ichnofacies as this deepening event. After the shallowing, this deepening event, there can be a time lag, and that time lag can lead to formation of a firm ground condition which can lead to glossy fungites ichnofacies. So, that can be another identifying feature along with the phases changeover. And sometimes, particularly when we are looking into the carbonate environment, that kind of gap can lead to formation of hard grounds, and those hard grounds can be associated with borings, some sort of incrustations or some other type of mineralizations. So, association of hard grounds, association of firm grounds, they can also be kind of indicators to identify flooding surfaces. So, the basic criteria to identify a flooding surface is definitely the phasis change, abrupt change in phases from shallower phases to suddenly deeper phases coming up over there. And to confirm that, additionally we can get these other features which can help us to convincingly interpret about a flooding surface. The shallowing upward succession within a parasequence that commonly indicates the accommodation space that was created is getting filled up at much higher rate than it was created. So, that is why the amount of basin space available is getting filled up by the shallower phases, the shallower environmental processes, they are coming up in the deeper part. So, this is exactly the same as we have discussed in case of progradation, in case of regression. Each and every parasequence indicates a phase of progradation. So, always during a progradation, the accommodation is less than the amount of sediment supplied. So, within this each and every parasequence, as we are going upward into the shallowing upward part, that indicates the accommodation space is getting consumed more rapidly than it was created. Just in contrast to that, when that parasequence is ending and it is changing into or starting with a new parasequence and that is terminated by a flooding surface. So, that flooding surface associated with the deeper phases just overlying the shallower phases, that represent a sudden rise in the relative sea level. So, definitely at that particular point across the flooding surface, more accommodation space is created and the supply of sediment is coming up at relatively lesser rate with respect to the rate at which the accommodation space is created. So, across the flooding surface, creation of accommodation space is in a positive mode with respect to the sediment supplied. So, accommodation space creation is at faster rate than it is being consumed by the incoming sediments. So, within one parasequence starting from bottom to top, we are getting a gradual changeover in terms of accommodation versus sediment supply. And as the parasequence is ending up, new parasequence is starting, we are getting another type of condition in terms of accommodation and sediment supply. So, when the parasequence is forming, gradually it is getting shallower up, the rate of accommodation creation is less than the rate of sediment supply. When it is ending up and starting a new parasequence through a flooding surface in between, that indicates more accommodation is created suddenly than the sediment supplied into the system. So, definitely in this way we can get several parasequences coming up one after another, they can get stacked one after another, and many a time we can get particular pattern of arrangement of those parasequences. As we have seen in the earlier case, the stratal stacking pattern which may get associated with a particular phase of shoreline shift. Exactly in the same way, when we are trying to define the parasequence from a particular succession, we are trying to define a succession of genetically related parasequences within a succession, they can form a distinctive stacking pattern. So, we are talking about the stacking pattern of the parasequences within a succession. So, when there is an overall regression is going on, we can expect a particular type of stacking pattern. When there will be a transgression is going on, we can expect another type of stacking pattern of the parasequences. So, based on that, we can get either aggrading, prograding or retrograding arrangement of the parasequences, resulting in different types of parasequence set. So, a parasequence set is nothing but the arrangement or stacking pattern of multiple parasequences under a particular phase of shoreline shift. So, it can be aggradational, progradational or retrogradational parasequence set. Let us understand one thing very clearly, that when we are talking about a parasequence, we are talking about individual prograding lobe in terms of bed to bed sets. and then each of these parasequence is stacked one above another during a particular phase of shoreline shift. So, it can be transgression, it can be regression, and during that entire phase of shoreline shift we can get multiple parasequences. So, within each parasequence it is a coarsening upward, it is a shallowing upward, but the stacking pattern of the parasequences can show aggregating, prograding or retrograding nature. So, let us take one example over here. This is an area in the marginal marine part where we are getting this coastal plain sand so much shallower, followed by shallow marine sandstone yellow color which is relatively deeper, and then we are getting a self mudstone which is further deeper. So, for the first phase, say for example phase 1, we are trying to understand the parasequence over here. So, as per definition, parasequence will indicate shallowing upward lobes, coarsening upward lobe, progradational lobes. So, what we can see for each phase, say for example this is phase 1, phase 2, phase 3, the coastal plain is prograding with respect to the shallow marine sand. The shallow marine sand is prograding with respect to the self mud. So, each and every facies association, each and every depositional system is moving forward, is prograding with respect to each other. And if I want to make a log over here in this part, what I am getting? I am getting initially a self mud which is followed by a shallow marine sandstone. So, definitely this particular arrangement can be called as one parasequence. This parasequence is covered up by this particular surface which is a marine flooding surface, because above that on this particular area, just above that particular surface we are getting the deeper facies is appearing. So, in this way if I look at this particular log, say you have made a vertical well somewhere and that well is represented over here. So, for each phase what we are getting in the lower part somewhere here, it is a dominantly shallow marine sand. Above that we are getting a flooding surface, and that flooding surface is overlain by the deeper facies. That deeper facies is overlain by again a shallowing upward shallow marine sandstone. That shallow marine sandstone is again overlain by another surface across which we are again getting the deeper marine facies, the self mudstone. So, each of them are coarsening upward, each of them are shallowing upward, each of these units are covered by a flooding surface. So, these are all parasequences. Each of them are indicating one parasequence. So, this is parasequence 1, this is parasequence 2, this is parasequence 3 and this is parasequence 4. So, when I am looking at individual parasequence, say for example P3, it is a simple coarsening upward, shallowing upward succession in terms of beds or bed sets, and it is covered by marine flooding surfaces. So, as per definition it is absolutely fine. But when I am looking at the overall succession, each of these shallowing upward succession, each of these coarsening upward succession is showing a retrogradational pattern, where at initial phase when parasequence 1 was forming, the amount of sand supplied into the system, the amount of shallow marine sandstone available into the system, and at the top part when I am looking into the parasequence 4, the amount of the shallow marine sandstone or the amount of self mudstone is completely varying. So, overall arrangement of the parasequences, overall stacking pattern of the parasequences is retrogradational here, where the entire system is gradually stepping back, gradually retrograding towards the landward side, towards the shoreline. So, this can be identified as a parasequence set, and since this is showing a retrogradational pattern, so we can define this one as a retrogradational parasequence set. But within this retrogradational parasequence set, what we are getting? Individual parasequences, they are coarsening upward, they are shallowing upward successions, and each of them are covered by flooding surfaces. So, this is one flooding surface, this is another flooding surface, this is another flooding surface. So, each of them are flooding surfaces and each of them are associated with abrupt deepening. As you can see over here, there is an abrupt deepening, there is an abrupt deepening over here across this particular surface. So, each of them are indicating abrupt deepening followed by shallowing. But when you follow the overall pattern, stacking pattern of the parasequences, they are gradually retreating back, they are gradually retrograding. Exactly the opposite of this can be observed when we are looking into a progradational parasequence set. Again, we are taking the same example, same setting where we are getting the coastal sand, we are getting the shallow marine sand and we are getting the self mud. So, again we are getting one parasequence over here, this is the second parasequence, this is the third parasequence, this is the fourth parasequence. So, when we are making a log somewhere here or maybe somewhere here, anywhere we can make a log. So, it will show each of them are indicating parasequences, but overall the parasequences are prograding forward. Within individual parasequence, it is a prograding forward, it is a progradational loop, it is a coarsening upward succession. And when I am looking at the overall arrangement, again it is showing an overall progradation with respect to the stacking pattern of the parasequences. So, when I am starting from here where we are getting a self mudstone and if I just move vertically, I am going into shallow marine sandstone. So, overall progradation is occurring over there. And within this succession, which may be in terms of several hundreds meter thick, there may be multiple parasequences. They are stacked one after another, each of them indicating coarsening upward succession, each of them indicating shallowing upward succession covered by a flooding surface. So, here this is a flooding surface, this is a flooding surface, this is another flooding surface and each of them in between this flooding surface, these are coarsening upward successions. So, I can take this one as an example of progradational parasequence set, where the parasequences are showing progradational stacking pattern. And exactly in the same way, we can get one aggradational parasequence set. So, here the shoreline is constant. So, overall the facies types are aggrading, but during the aggradation again we are getting similar kind of progradational lobes forming for each parasequence. So, you are getting one parasequence over here, we are getting second parasequence over here, the third parasequence over here, the fourth one over here. Each of them are separated by the flooding surface. So, this is the flooding surface which is indicating abrupt deepening. So, in smaller scale, when you are looking in parasequence scale, there are fluctuations in water depth like this, but when you are just trying to look at them in terms of overall shift of the shoreline, it is not shifting at all in this case, as the parasequences are stacked in an aggradational pattern. So, in this kind of condition, we get stacking of multiple parasequences forming aggradational parasequence set. So, parasequences, they are commonly identified as relatively higher frequency building blocks within a sedimentary succession and commonly are associated with overall trends of coastal progradation or retrogradation. Accordingly, we will get different types of parasequence set, we will get different types of stacking of the parasequences. So, they may be identified as part of larger scale system structs. As we have seen the progradational parasequence set. So, definitely that kind of stacking of the parasequences can be identified within LST or maybe within HST. We can get the retrogradational parasequence set that can be identified within one TST. So, the parasequences and their stacking pattern can be a building block for identifying or demarcating system structs which are relatively larger scale feature. So, we can study the parasequences in relation to the discrete cycles of changing depositional trends, as within individual parasequence we get change in terms of depositional trend, we get change in terms of the flooding surface, as well as we can study them in terms of parasequence set where the depositional trend is changing from the bottom part to the top part of the parasequence set in terms of aggradational, progradational or retrogradational pattern. So, the patterns of the stacking of parasequence set are commonly used in conjunction with the boundaries and their position within the sequence to define different system strats. So, many times many workers they use this combined way, defining parasequences, defining parasequence sets to define or identify the system strats with proper boundaries. So, these are some of the references that you can further go through to get detailed insight about the parasequence, its concept. So, thank you everyone.